Hello, this is Mr. Standerson, and in this lesson we'll go over the details of adding vectors using their coordinates. This might be a vector given with a grid on a graph paper, or it might be a vector that you break down into its components and then find the resultant. So to get started, I want to review a little bit about the vector components, and you might be given a list of vectors that's similar to what you see in the middle of the page here, where there are different vectors that either have x or y components or a combination of x and y like e. So notice here this has an x component of 2 and a y component of -1, 2, 3, 4. So those vectors can be combined together. If we're combining vectors, in this case like C and F together, we're going to use the chart and we're going to look at vector C, which is right here, and vector F, which is right here, and we're going to combine them together in the order that they indicate using the tip to tail method. So I've already drawn in vector C here, which is 1, 2, 3, 4, 5 across, connected with vector F. So the tail of F connects to the tip of C, and I just draw it just like I see. It's 1 over and 3 down. Now that gives me a new ending spot. So my new vector is actually going to be a combination of C and F. So I drew it in orange here. From the start to the finish, I have now a new coordinate system. So I'm going down 3, 1, 2, 3, down in y, and over 1, 2, 3, 4 in x. So when I look at my x and my y components now, that is the information that I'm going to choose. My x component is 4. Why is it 4? Because it starts in and moves over 4 spaces or 4 units in my grid. The y component is -3 because from where we start, which is right here, we're going down 1, 2, 3 places. Hopefully that makes sense. Now when I want to find my resultant, I'm going to use the Pythagorean theorem and find this hypotenuse. The resultant is the hypotenuse in this case. So when I take a look at that, I'm going to move this box here off to the side. I have a square root of 4 squared plus 3 squared. So basically a 3, 4, 5 triangle. My hypotenuse would be 5, and therefore this spot here would also be a distance of 5. Now the tip to tail tells us the direction, and that's important also. All right, taking a look at the next example, very similarly, I'm going to look at the vectors A and E. I'm going to add those together, A plus E, using the tip to tail, putting A first, and then connecting that with E. My new start to finish is the orange vector. Pause the video real quick and figure out what that X component is going to look like and what the Y component is going to look like. Unpause the video, please, and let's check your work. So here we go. I'm looking at my components, -1 and -4. Putting that in the Pythagorean theorem gives me a hypotenuse of 4.12. That is now the resultant length. Taking a look at other examples, if we add more than one vector or more than 2 vectors or 3 or 4 or however many, we can do the same process by keeping track of the components, the x and the y components. I'm going to encourage you to build an x and y table for each of the vectors that we look at. We're looking at vector A, D, and E so that we can figure out what the total x and the total y is from our start to our finish, building that new triangle. So here we go. We're going to build the triangle down 2 and over 2. So this becomes 2 in the x. After I combine all of these vectors together, I get a total of 2. And -2 in the y. Similarly, I'm combining all of the y values together. And when I say combine, I'm simply adding them together. Then my resultant is the hypotenuse using the Pythagorean theorem. So in this case, it becomes 2.8. Please let me know if you have questions about this, but this is the general process, connecting all the vectors from tip to tail and continuing to combine them as needed. So if we had another vector here, we would just add in another vector from where we stopped and keep going. Please let me know if you have questions along this process. And my last thing that I'm going to talk about is the way we measure the angle of our resultant vectors. Now remember, this is going to be for the resultants. And if you have a protractor, you can use that. Even if you don't have a protractor, we're going to be using notation like 30 degrees north of east. You can approximate that 30 degrees without a protractor, but finding it accurately with a protractor is also helpful. Now, why do I need these directions? Well, the vector itself is pointed in a certain direction, so we need a reference line. In this case, the east is our reference line. So I could imagine an east-west line right here, and then I'm going 30 degrees north of that. Remember your cardinal directions. We have north, south, east, and west. So if I'm moving 30 degrees north of east, I'm starting on the east line and I'm going north for 30 degrees. That's what that designation indicates. Okay. Of course, I could also measure it from the 90, and then I would just be moving 150 degrees. So if I measured it from 90, I'd be going 150 degrees to the east of north. So I could flip those things and I would still get the same direction. All right, so usually you can pick whatever makes the most sense to you and stick with that. All right, let's look at this example over here. All right, so once again, it says west of north. So you guessed it, north becomes my reference line. So I'm just going to sketch that in. And I'm going west of that, so I would start at north and go to the west, and I'm going 30 degrees west of that line. Okay, that's really all that those indications mean for direction, and they help us figure out our resultant direction. So if I take a look at these examples, notice that there's two ways of measuring this. I could measure 25 degrees west of north, so this becomes my 25 degrees here, or I could go north of west, and I can make west my reference line right here, and I'm going to get the same amount of direction, but it is a different angle. So that reference line becomes really important as to where you're starting and where you're measuring from. Now, when we put this all together, you might have multiple vectors. So here's a vector 1, tip to tail with vector 2, tip to tail with vector 3. Finally, our resultant vector from start to finish is going to be in this general direction. Now, I can measure the angle, and I'm going to still need a reference line. So I'm going to put east as my reference line. Okay, therefore, when I measure that angle from east, I'm going north of my east reference line, and this protractor says about 23 degrees. So these are the general basics of finding your angle of your resultant and also finding all of the components of the resultant. All right, lastly, this also works with magnitude, and scale, remember, is really important. So you might need to indicate your scale when you're drawing out your graphs. So just be careful of that, double check your scale as we're going forward. Hopefully now you have a better understanding of how to add vectors graphically using the distances that it gives and the tip to tail method. You can now interpret a certain number of degrees, north or south or east or west, of your reference direction, north, south, east, or west. You can now break vectors down into x and y components and build an xy table. Calculate that resultant by adding all the xy components together and using the Pythagorean theorem. And then you can use SOHCAHTOA, sine, cosine, tangent, to solve for your direction. That's our basic process. Please reach out if you have any questions. Thanks.